Hi everybody, welcome to our webinar. My name is Sarah Lynch. I'm the marketing manager at PSIM, and first of all I want to thank you all for coming to our webinar today. We're going to talk about modeling, design of motor drives, as well as performance evaluation with efficiency maps, and all of that we will do with a tool chain consisting of PSIM and JMAG software. So as you can tell, we have a lot of content to cover. Now I quickly introduce our presenters. As you might know, we are co-hosting this webinar today with PowerSys. PowerSys is the exclusive distributor of the JMAG software in the USA and in Europe. And they are represented today by Dheeraj Borba. He is a senior electromagnetic engineer and an expert in motor design with JMAG. And in the background, he's supported by Ryoko Imamura and Sainang Su, who will be able to answer questions in the chat during the webinar. And on our PowerSim side here, we have Albert Dunford. He is our application and support engineer and a PSIM specialist. And in the background, we have our motor drive specialist, Mark Kinn, and he is going to be able to answer PSIM-related questions in the background or help us, since he also built the model that we are looking at today. And with that, my introduction here is complete, and I will give the talking stick to Albert, and we can start the webinar.
Thank you, Sarah. So I'm just going to do a couple slides here, and then I'm going to hand over to Dheeraj, and then we'll kind of get started on the meat of this presentation. So let's kind of give you the punchline first. This is what we're going to try and generate in this webinar, or not try, we are going to generate in this webinar. We're generating efficiency maps of a motor drive system. That includes the motor and the inverter and its operation at different torque and speed set points. So the motor models that we're using include copper and iron losses. The inverters that we're using, we're doing switching and conduction losses of the switch and the body diode, and these are full actual real simulations, you know, with switching, with closed loop controllers, with space vector PWM, with whatever else is going on, and we're going to generate these plots. So this is, we can see the main efficiency points here, the gradient of red. And so this is of the full drive system. And of course, we've also got it separated out to just the inverter. And then we also have the motor itself. So again, when we're driving the motor, we're looking at everything. We've got full closed loop. We're implementing max torque per amp control. We're implementing field weakening. We're implementing max torque per volt control. We're using space vector PWM. We can change all of these things. And when we're doing the inverter, switching back a slide here, we're using the junction temperature is being considered of the device, and we're also considering the voltage drop across the device during conduction. So it's a full closed loop system with about as much detail as one needs to put in. And I think this is the simulation that we used. We've got a JMAG model here of the motor, we've got the inverter set up here, and we've got the closed loop system down here. And as I said, closed loop controllers for field-oriented control, so we're closed loop on ID and IQ, and we've got a torque reference control. We're using thermal loss models. We're doing, yeah, you know, this is what we're going to get to towards the end here. So over the next, I guess now 40 minutes, 50 minutes or so, this is what we're going to cover. And now I'm going to pass it over to Dheeraj, because he is going to explain all about this JMAG, the JMAG PSIM RT model, machine model that we're using here to provide us with all of our information with regards to this simulation.
All right. Thank you, Sarah and Albert. All right. Hopefully you can see my screen now. And yeah, that shows the agenda for the seminar today. And as Albert said, the first part of the session will be looking at the introduction to JMAG part and trying to generate whatever data we need to pass it on to PSIM. Pictures talk more than words, so I just included in the agenda what we'll be going through. So we will have this electromagnetic analysis, efficiency map of the motor only, and then capture as much of the detail from the FEA into a lookup table format with JMAG RT, and then pass it on to PSIM for further analysis with motor and in-motor together. So with that, let me jump into the introduction for PowerSys. We are primarily a software and services company, focusing more on the electrification challenges of current industry. Most of our current focus is on EV and grid side, and of course EV includes aerospace electrification challenges as well. We are primarily in the process of, in the field of providing high-end engineering services, advanced and adaptive simulation platforms, and more or less in terms of expertise, background expertise on all these topics. Our company is about 18 years old now, and we have 8 offices globally with over 50 employees. I'm located here in our Detroit office near Detroit, USA, and we also have a San Diego office in California. And jumping on to JSOL or JMAG, which is primarily what today's webinar is focused on. JMAG Group is part of JSOL Corporation, and they are located out in Tokyo, Japan. And they have been providing this FEA software, simulation software for electromechanical analysis, and it's been almost 3 decades now. So it's quite established in this field. Also one of the largest FEA tools in the Japanese market, and also expanding into other markets now. All right, so what does JMAG include? What's possible with this? So to look at the JMAG toolchain, we have different tools that start from the initial sizing or analysis phase all the way to a system level analysis. The first part is what we call JMAG Express, or Express Online tool, which is capable of doing template-based analysis on motors, and also some template-based model generation for transformers. And then the models can move into JMAG Designer, which is a full-fledged finite element analysis tool. It's primarily more focused on electromagnetics, but it also supports structural, thermal, and a few other aspects. And then which we move on to the JMAG RT, which is what we'll be focusing mostly on today, which is basically extracting the data from FEA into a usable format that can be applied for system level simulations. All right, so with that, let me jump into the machine that we'll be using today and how to build that machine using JMAG Designer. To give some idea, this is the application we picked our machine from. It's from a 2010 Toyota Prius. A lot of analysis has been done on this, and a system level breakdown analysis was performed by Oak Ridge National Laboratory, and this is coming from a report that's been published and available on the website. So here's a link if you like to go over and check some of the details yourself. This figure here is the entire circuit representation of what's happening from battery to the motor and generator set. It has both motor and generator, and they're mounted on the same axle. This picture is actually coming from an older report, but the system is similar. They supplement the internal combustion engine. Here, MG2 is referred to as the electric motor, which is what we'll be focusing on, and MG1 is the generator. And yeah, as I said, so this is the section that we'll be focusing on today. The rest of them we'll exclude. But of course, if you're building an entire system, it is also possible to the same schematic that we'll be presenting today. So we pulled some of the specifications for that motor, which is the MG2, from that report. The peak power for that machine is 60 kilowatts. And the peak torque, which is at the corner speed or at the constant torque operation, is at 205 Newton meter. And the speed's also based on the information from the report, as well as the system level specifications, which is the DC plus voltage, the maximum current possible. And then, as I said, they did a complete breakdown, so they listed some of the dimensions, the winding configuration, the number of turns per coil, the strands available, and the phase resistance. So using all this information, we were able to recreate the geometry in JMAG Designer. we are looking at the CAD model for the full machine with the phase winding color coded there. Of course, there's still some information that's unknown, primarily on the sense of what type and grade of material was used, and the PM residual flux density is known, but the material is not known. And it also shows that there's a steady state operating temperature somewhere around 100 degrees Celsius. So we picked 110 just to be on the conservative side. So we built this model in JMAG. And then for the next part, I will jump into some of the demo, which shows how this model is set up in JMAG, and then jump into the results. So what you're seeing here is the interface for JMAG Designer. On the right side, we have Toolbox, which is where we have the material database and all the conditions set up for the analysis or the study. And on the left side, we have the project manager, where we have the CAD model that we bring in from any CAD tool, either inbuilt from JMAG or other third-party CAD modeling tools, and then the type of analysis we run. So initially, I want you to notice that all the material is, all the parts are set as air. The material properties are not set up, so we'll go through this demo to go through the process of assigning the material and conditions for the study. So initially it's air, and on the right side we have this material tab, and with that we know the winding is copper, so we can search for that, and assigning is simply drag and drop it onto the part that it's supposed to go on. And I'll repeat that for all three coils. We have phase A, B, and C. And then we see that copper is assigned to coil. And the next step, I'll go to the lamination. As I said, we pick 35J and 230, which gives a close enough performance from the report data. Again, drag and drop. And I've pre-assigned some of these, so it'll populate automatically, but it's laminated with a stacking factor of 96%. And I'll do the same thing for the rotor.
Duraj, while you're doing it, there's a couple of questions in the chat here with regards to magnets and other things. So can we coat the question here is, can we coat the magnets with a surface finish like aluminum flash or epoxy in the design tool? And then there's another question about rotor magnets being pre-magnetized or magnetized in situ. If those sorts of things make a difference, can those be included into the machine model?
I think the first question is more on the material side. I'll have to get back, but I think if it's physically modeled, like the coating, the thickness of the coating is physically modeled in the CAD geometry, and if the material properties are appropriately assigned, I believe it should be possible, but I'll have to double check. And the second one, it's pre-magnetized or being magnetized in the model itself. It is definitely possible to simulate that. In this case, we are using pre-magnetized, but we can capture the magnetization process itself and use that magnetization for the analysis. I hope that answers that question.
I think that's a pretty good answer. Thanks, Duraj.
Welcome. All right, so moving on with the demo here. So next one, I picked a magnet material that has the BR that's close enough to the published value, and also picked the temperature there as 110 degrees Celsius. Of course, this changes the BR value to the exact measured one. And for the magnetization, we see that all the vectors are aligned to the x-axis, which is the default value. And to assign a specific value, what we can do is select a geometry edge and set it parallel to that edge. Selecting that edge shows the vectors change. Click OK, and we'll do the same thing with the second magnet. Once again, zooming in there and select the edge. That'll assign the magnetization direction. And then that is all there is for the material setup. So we have all the parts assigned to specific materials now, and we don't need to create any air region in JMAG. That'll be automatically assigned. And the next step now is to move on to study conditions. So it is a 1/8 model. We only model one pole, of course, to reduce the analysis time. So first step, we'll assign the periodic boundary condition. Of course, it's a 45-degree model, and it's a one pole, so it should be anti-periodic boundary, meaning the other copy will be opposite polarity to this. And then we want to indicate which parts are rotating. So I'll pick the motion condition here for rotation assigned to the rotor core and the magnets. And I've created a variable beforehand setting RPM, and that's matches with the corner speed 2800 RPM. And give the name, click OK. And the last thing we need to assign is the output, which is torque. We need that calculation also on the rotor. We can either select all the parts or we can also go and pick the motion region that we've already assigned to. Okay, give that a name. And that's all for the motion condition setup. And the last thing we'll do is assign the winding direction. So we can add a winding tool there and select the region that corresponds to winding. All we have to do is select one part of the group, a single coil, and set the number of slots and the pole, and that will determine where the other slots are and pick up the appropriate winding configuration. So we'll go to the winding setting, add a three-phase winding there, and set the number of turns and phase resistance, which is something we got from the Oak Ridge National Lab report. And then the second tab here shows the winding path, or the winding go unwritten path. You will select the three-phase, and we can use it at auto, which is currently, and the coil pitch is set to 1. We can either use the maximum coil pitch or specifically specify the coil pitch if it's a short pitch. In this case, both are the same, right? So click OK there, and now you can see all the winding setup is completed. So it will show the current directions for each of those coils. So that's all there is with the model setup, and of course there's some little bit of work to do on the tuning of the mesh, but that's not something I'll focus on now. And we can move on to running the analysis and looking at the results. All right, so with that, I ran the model, and on the top here, we see the flux density distribution at rated operation. And I performed this analysis at different current amplitudes and different current angles, and the torque waveforms are plotted here. As you know, it's an IPM machine, so it has both PM and reluctance torque components. So the optimum or maximum torque position is somewhere in between 30 to 60 degrees, usually for IPM machines. So if we identify each of those points, we see the maximum torque there, and we can plot that out as a function of the current amplitude. Here 200 amps is a rated current, so we see it's almost linear until then, and we see a little more saturation after that, impact of saturation on the torque after that. What we also did is at this rated current amplitude, we can look at the entire torque versus current angle waveform, and using the data of the permeability of the entire stator and rotor steel, we can freeze those values and then run an analysis to separate out the PM and reluctance torque components here. So we can see in this total torque, that quantity is the PM torque as a function of current angle, and that quantity is the reluctance torque as a function of current angle. And then if we look at the MTPA point, we can plot the rotor position dependent torque waveform, and we see that, of course, there's some torque ripple, which is expected. In this case, the average torque is 207 Newton meter, which is close to the published value of 205, and the torque ripple is about 11.2%. So this gives a high fidelity model, our output value of the torque as function of the rotor position. That's coming from FEA. Now, next is the loss calculation. If we go into the different types of losses available, typically these are the items that we consider. And in this case, the copper or Joule losses are dependent on the material optical resistivity and on the excitation frequency, because we have fundamental and probably switching harmonics. Of course, in this case, we did not model switching harmonics in JMAG. That's something that will show up in the PSIM model. And then the mechanical losses are analytically estimated, in this case, which are the bearing friction, rotor windage, etc. And then the iron losses there's multiple ways to calculate this in JMAG. Particularly in this case, we've used the FFT method. That's basically looking at the historical data of the flux density in each mesh element and taking that, applying FFT, looking at the frequency, dominant frequencies, and then the data is compiled using the material loss characteristic provided by the manufacturer. And one important point to mention here is, since it's a frequency-dependent quantity, of course, in general, losses are the carrier frequency or the PWM frequency impacts the iron loss. And then the last step is to look at the efficiency map generation. And of course, I have to point out this is for motor only. And this is something we can do in JMAG. There's specifically a efficiency map analysis that we can select. The interface looks like this. There's the speed priority mode and accuracy priority mode. Of course, as the name describes, speed priority meaning it can run faster with fewer number of points. Accuracy priority is more focused on getting a higher level of accuracy in the loss calculation. So in this case, I'm using speed priority mode. We'll set the number of poles and give a few data points for this model to run at and estimate the entire efficiency map. So with that, it'll take a little while to run, and afterwards we'll set up the inverter rating, which in this case the bus voltage is 650 volts maximum, and the current amplitude, fundamental current amplitude, is 200 amps, or the line current amplitude. Using a very basic motor control, max power or efficiency, and we can either pick motor mode, motor plus generation mode, which will give both quadrants. And we are also considering something called an approximate PWM iron loss, which is a approximate value, as the name suggests, and it is based on the bus voltage and the carrier frequency. A more detailed value of this one will be obtained from the PSIM with the complete switching model and the inverter model. And we also analytically estimated the mechanical loss and put a loss factor of 15 watts per 1000 RPM. So with that, this is the efficiency map that comes from JMAG, and as we can see, it gives a complete torque profile over different operating speeds. And we can also add data points on this efficiency map if we want to look at individual loss components. So in this case, for example, we can pick a different operating points. We can start with a high torque, low speed at the point, and it will give this pie chart at the bottom. I've identified the different color-coded loss components here. Of course, it's low speed and high torque, so the current is high. So we have the gray piece of the pie is larger, which is the copper loss. And the other components are quite small. So we can repeat this process, add more points at low torque and low speed, and somewhere in the middle at the higher efficiency point, and something at the high speed, low torque operation. So we can see the data at different points like this. We can export all this data into CSV and post-process if we need to. And we can see that as the speed changes and the current changes, there's different amounts of losses in the stator, rotor, and the copper, and also the PWM approximate points. So here, yeah, it shows the points where this data is coming from. And so that's about the analysis that we can do in JMAG. So for the next step, we need to move on to PSIM. Oh, sorry, the RT. So that's where we'll jump into generating the RT model from JMAG. So first,
maybe before you move on, there is a couple of more questions
Sure.
that are a little bit more on the basic part before we go to the JMAG RT.
Here, Sarah, I'll read them out for him. So there's the questions. So the copper losses, the losses that you're calculating are those in all recent versions of JMAG? There's a question about which versions of JMAG those losses come in, like copper losses, switching losses, and iron, etc. Are those those are all in recent versions of JMAG, or were there changes there?
There were some changes that specifically with the approximate PWM losses, but the copper losses, they've always been there in every version, I suppose.
Okay. Excellent. And then there was a clarification, I think, about the switching again, the iron losses in the machine. So you're taking an FFT of the approximate PWM waveform, and then from there kind of calculating what the losses will be.
Mm-hmm. That's correct.
Okay, perfect.
See a lot more questions here. I'm sure we'll answer them one at a time.
You can answer some of those when I'm presenting. Just type into the chat.
Yes. Yeah. All right. So let me jump on to JMAG RT here. So first, let me start with what is JMAG RT and what is it doing. So as this graphic indicates here, basically we have this 2D or 3D model in JMAG Designer, which is a full FEA model with the high fidelity data of saturation, leakage, inductances, and everything. We'll run this model at different operating points. And of course, this is just a depiction of what could be. Typically, the rated current was 1 per unit, and we'll try to get around 2 to 3 per unit data. So we capture the saturation in this highly nonlinear region, and then all the data is compiled into a table format, which can be read in by third-party tools or even JMAG RT viewer. And that compiles an output block, one-dimensional block, which we call, or a table. So all the process to generate these operating points and packaging is all automated through the JMAG RT interface. And there's different levels of fidelity. We can either do a lump parameter, spatial harmonic, or a lookup table model, or an LDLQ table model. I'll go through that in a little bit in the next slides. So then the question comes to, why do we need to use JMAG RT? There's already existing motor blocks, either PMSM or induction, whatever. There's motor blocks in the existing control circuit simulators. So here I'm showing an example from PSIM. This is the data that we enter. This is usually what we call the lump parameter model, meaning we have the DQ equivalent circuits, and we have the inductances and iron loss are fixed. And then we have the torque calculated from this equation, and this is how the torque versus current looks like. It's linear when we specify a single value for LD and LQ. And then there's a nonlinear model, meaning these inductances are now variables. They're dependent on current amplitude. And we can also create that with existing models. In a sense, we can give the lookup table for LD, LQ, and then these two quantities become current amplitude dependent. And we see the torque changing as current increases because the inductance, due to saturation, inductance goes down. And then if we look at much more higher detail, even the PM flux is dependent on the saturation. Usually that's not something we capture in the lump parameter model. And also these inductances are rotor position dependent, meaning so far we look at average values, but not rotor position dependent values. So that's where the full spatial harmonic model comes in. Here we have LD, LQ are both current and position dependent. And we also have the mutual inductance and zero sequence components. This is due to any leakage effects in the model. And the flux linkage is current amplitude dependent. And the torque is directly obtained from FEA, which includes the full rotor position dependency. And with this, we can see the third line here, again, plotting as a function of current. As the saturation increases, the leakage increases, and we see the impacts of those in the high current region. In addition, if we are specifically using that for a control development, control circuit or control algorithm development, the lump parameter model, the PI gains cannot be tuned accurately to handle those transients. So the blue waveform is coming from the LDLQ table data, and the orange one is coming from the spatial harmonic, which includes all these components. So a properly tuned controller can nicely handle the transient. Using the same controller without proper tuning of the gains, we can see that it's a huge spike there. And in addition to that, as I mentioned, there's a rotor position dependency. And the average model we see is a constant torque, while the spatial harmonic model, we can see all the torque ripple being captured as the rotor rotates in the spatial frame. So now, how do we create this JMAG RT model? There's multiple ways of doing it. Of course, as I said, there's a template tool, which is very quick analysis, and it can do a simple LBLQ table model, which is quick. And then we have a model that can be created from JMAG Designer, which includes all the spatial harmonic components. And we can also use some experimentally measured data and export it as a CSV file and give it to the JMAG RT interface that can create the RT model with the data. And the last one, we have a sample database on our website, which can be used to download some of the samples at different power levels, different machine types, and you can use those in your control circuit simulation. And the last step here is to go and look at how this RT model is generated. And so this is the RT maker interface, or JMAG RT library manager. So if we go in, click on new, there's different types of machines available, machine models that are available to pick from. And in this case, it's a PM machine, so I'll leave that there. And we'll select the spatial harmonic model and give the path for the JMAG file coming from JMAG Designer. On the first tab, it's more for the user information, so we'll give it some name, select publish here, and again, this is being written to the file for end user. When we look at the RT file, we need to know what it corresponds to. So I'll specify the speed, current and voltage, and some few other information. And then the second part here that we publish is basically the settings used to create the file. So we'll set that on the second tab here, on the Create tab. Set the number of poles, number of turns, and phase resistance. And previously I showed the circle or the DQ plane data points for current, or the operating points. So we can simply create that by specifying rated current, and it will automatically generate the point sequence at different current levels, in this case 3 per unit. And also the current angle, we're only looking at second and third quadrants there. And we'll allow iron loss and give a maximum speed, and it will automatically determine the range of operating speeds to calculate. One more change I'll make here is set parallel processing. Of course, this is to speed up the calculation. And at the bottom, it shows the number of cases or number of designs it will run through to generate this lookup table. And click OK, and then click on Create Models. It'll take a while to run. And of course, I've generated this previously, so I'll skip through. And once it's done, the next step is we can go into this control circuit simulation export tool, and we'll pick the target as PSIM and click OK, and that'll export all the files necessary to run with PSIM, and we'll copy those into the corresponding folder. All right, so I think that's all the slides I have on the JMAG side. I'll hand over the ball to Albert, or do you want to answer questions right away?
So just a quick couple seconds here on about PSIM. PSIM has been around for 25 years. It is a power electronics simulation tool specifically designed for power converters and motor drives. It occupies the space in between the simulation control style tools like Simulink and the device level tool like Spice, and it should be a one-stop shop for all of your power electronics simulation needs. So you can do all your control design inside of PSIM, and we can move towards nonlinear models that replicate what a Spice model can handle in PSIM as well. Widely regarded for simulation speed, result accuracy, and robustness of the engine itself. This is everything that PSIM can do. Today we're looking at the motor drive aspect, digital control, our motor control design suite, and our link obviously with JMAG. And here we go. So once you get that, so we've got a motor control design suite, and we're going to use the motor control design suite to take that JMAG RT model, and we're going to close the loops around it. So we're not going to have to sit here and figure out what the ID, IQ controllers need to be for the PI controllers for ID, IQ, the torque or speed loops. The controllers are design, the design suite will generate stable controllers based on the motor parameters, inverter parameters, and switching and sampling speeds that you're working at. And then obviously you can then edit the schematic after the fact once it's been generated. So why do you need the motor control design suite? Well, in a motor drive itself, there's lots of things that one needs to consider, and most of those things require a working machine model, and to get a machine model to run properly, you need to then also have a working motor controller. You can't just force theta, you need and ramp up a PMSM. You can't just slap on. It's not an induction machine. You can't do anything you like with these things. You need to have with a PM machine, you need to wrap it up properly. You need to have proper closed loop systems on it. And then if you're running with advanced control algorithms like max torque per ampere control or max torque per volt control or field weakening, these things require closed loop controllers. So, DC capsizing, component selection, considering EMI, what sort of switching speeds we should be working at. These things require closed loop controllers. So a lot of designers I know who work on the power stage are not necessarily the guys coming with the control algorithms that are going to be used in the end products. So then we end up with a situation where there can be someone who's trying to evaluate an aspect of the power stage, and they're waiting for someone to come up with a closed loop controller. Or they're looking at optimizing switching speed, or they're looking at all these different things, and it requires a closed loop controller. And if you don't know what you're doing, or if you simply need to iterate many, many times, the design suite allows you to come up with a closed loop system that's going to work. Maybe it's not the one you're going to use in the end product, but it's going to work, and it's going to allow you to do your work. So essentially, here's are the input parameters on the left-hand side. We've got DC bus, switching, max current of the converter, the rate. In this case, we're looking at the speed load. We're running with a constant speed load here for generating these curves. The motor parameters are here. In this situation, we have a bulk LDLQ, but the actual control suite, we can run with a linear LDLQ, or we can run with a nonlinear LDLQ. We also have, so these are and then we have got the motor controllers down here. So all you need to specify for the motor controller is essentially the sampling rates and the desired cross frequencies of the current and torque control loops in this case. Okay, and so we see on the right-hand side the outputs of this design suite, what we've calculated here. Most importantly here is the PI values for the current controllers and an integrator value for the torque controller. So the goal here is to stop wasting your time designing or waiting for other people to provide controllers for any major or minor change in what you're trying to study, and to use you can use the provided control values for initial design considerations, or then once you get towards final end goals here, final end product, you can easily modify or incorporate your in-house controls and algorithms. The other aspect of the simulation we're looking at here to generate these loss curves is the thermal models. So the thermal models calculate switching and conduction losses. The conduction loss will be observed. So we'll be able to look at a voltage drop across that FET or IGBT. The loss will change as the junction temperature will change. So we can either fix TJ by just fixing it to a certain temperature, or we can put in a thermal equivalent circuit for a heat sink. So the underlying switch is ideal, which allows us to have faster simulations, and the data is based on data sheets. So it's relatively straightforward to add new models or to edit the models that are there to get them to better represent what you have in the field. Next slide. So here's a look at a silicon carbide device. So you can see all the curves here, voltages, losses versus with different curves for temperatures and different currents. So conduction losses and switching losses are getting scaled in this case with temperature or with RG values. So the other aspect of this will be the scripting that we've implemented. So scripting allows you to work smarter. So the simulations for these efficiency maps with the scripts, they ran in 42 minutes. So we did over 100 simulations, and in each of those simulations, we extracted the losses on the inverter, the losses on the motor, and the loss, and then combined them to look at the total losses of the system. And it was easy. It was relatively straightforward. We can easily modify the script to incorporate comparing different devices, different space PWM control techniques like space vector or DPWM. We could do things like change the DC bus cap and see what the change in ripple currents are there. We can change switching speed, etc. And it's easy to save the data set, so we don't need to, and then add in an automation of the analysis. So we don't need to rerun the simulations all the time if we want to just reanalyze the data set in an automated way. And so there's a question I see that just popped in. Does the simulation software show machine operation when the magnet orientation wrongly inserted during rotor building? So that the rotor building aspect maybe is part of what happens when you're looking at the machine in JMAG. But in PSIM, in the simulation, if you lose synchronization with the rotor, if you're not controlling it properly, you will see issues in the simulation. You will see issues with the torque developed, and you'll see issues with the shaft speed if you lose synchronization, if you don't have a proper controller. If your controllers aren't stable, you will see that in the simulation for sure. But then if you're using the motor control design suite, that shouldn't be a problem. Okay, so the workflow is essentially we're going to take that RT model that Dheeraj came up with, and we're going to basically insert it into PSIM, and then we're just going to run these simulations. It's as easy as that. So let's have a little look at some simulations here, and let's have a little look at some of the results. So again, this is the simulation that we ran. Let me close the library up on the side here. So we are, again, we've got a basic DC bus. Here's that JMAG model. So all we have to do is point to that RT file, and once that's in there, we're pretty much ready to go. And then we're coming out of this model, we're bringing out LD and LQ here. We're bringing out the copper and iron losses. And then we are bringing LD and LQ back to the current controller here. So as many of you probably know, with the changing LD and LQ, you need to change the gain path. So we can see that in the current controllers here, what's happening with these PI controllers. As LD and LQ change, we are changing the gain coefficient of these PI controllers. Coming back one level. What else is going on here? We are implementing max torque per volt control, field weakening, MTPA, and we can also use this little tool here to calculate and look at what the expected torque speed curves are and power speed curves are based on this inverter setup. So we can generate these little curves for us. And we can also go ahead and run this simulation. Now I just need to make sure that I've got it still set up to run correctly. Yeah, so we can just run this. So this is a single point simulation. We can see that we've got a constant speed load. So if we're doing these sorts of simulations, we need to be using, if we're trying to generate an efficiency map, I would strongly recommend running with a constant speed load. That way you can set the speed of the machine and you don't need to worry about inertia and accelerations of the motor. They're faster simulations that way, so we can hit torque set points. So we're just now controlling the torque of the machine, and it's going to be a lot easier. We can look at some currents here. What else can we look at? There's ID. We can look at LD down here. So yeah, while this is running, so I'll stop that for a second here. So that's, you know, a single point simulation. And then what the script does, if I pull that over, a little folder, is we then run that 100 times over. So that took, to do all the simulations will take right around 40 minutes or so. And then from there we can then, that's where we generate, where's my little figures? And we're getting back to these figures here, where we've got, we can look at a combined full drive, inverter only or motor only aspects here. So of course, so the script that we wrote, you know, is easy to modify. If we look at the script itself, we can see we've got a range, basically an array of speed values and an array of torque values, and we just work through them. And then we've also got another array here where we check to make sure that we're not going over the torque command limit at a specific set point. So this simulation, I was just simply running one device at one switching speed with one type of control method. The other simulation that I put together here, and I did a few scripts on this one. This one, I've set it up so that we can compare a 6-pack device versus discrete devices. I've also got it set up so that we can compare different control methods. So in this case, space vector PWM or DPWM. So these ones are set up to run that way, so we can compare efficiencies between different methods. And as you can imagine, we can cycle up from here looking at different switching speeds. We can look at all sorts of different things this way. And it all can be automated via script. So in this example, when we look at the parameter sweep I set up, let me just grab those outputs. So these are single operating points. So here's the drive, and I've got them labeled here, and this was all automated. This waveform setup and look at here is where we're extracting waveforms from essentially my output files are all here, and I extracted the efficiency waveforms of interest, and we can see a specific CM600 device, 24A, with different space vector PWM versus discrete PWM. These two lines here. We can see, so we're ranging on the drive itself between 87-ish, I can measure that actually, between 86.9% to up to 89% at this particular operating point. So if we wanted to run all these situations through all of the different scenarios, torque speed curves, we'd be looking at maybe running it overnight at that point. But it still would be a totally automated situation, and we end up with all those graphs at the end where we could easily compare all these different process or design aspects. Okay, so I think that's all the information that I was hoping to cover, and now I can look more to some of the questions that might have been coming in. So yeah, questions. I recognize we've got we've a few minutes left here before we hit the top of the hour. Yeah, I'm open to questions now. Let me just also, while we're thinking of questions, I'm just going to pull up one of these other simulation results so we can see what was included here. So if we look at the shaft speed of this, so this is the developed torque of one of those simulations. We can see the impact of the spatial harmonics here. We can see the stability of the control loops as well. So we can see that we're remaining stable here in the presence of that harmonic content. What else can you look at? So these RTT files, this is everything that the RT model is reporting back to us. So LDLQ, for example, we can pull those up. Fluxes, all that kind of information is all here for us to look at. Can you model rotor loss versus DC link voltage switching? Yes, of course we can. This is a working motor drive. This is a working inverter. So if we change the DC link voltage, we could run all these simulations all over again with changing DC link voltage. We could change, if we increase the switching speed, we'll see an increase in the switching losses. All of that information is easy to see. And comparing device to device, IGBT versus silver carbide, one manufacturer's discrete device versus a 6-pack. That's all can be included. And you can include a battery model if you want to as well, of course. Again, this template is now ready for you to edit. So if you wanted to put a battery model here, by all means, put a battery model here. So let me just pull back my. Yeah, we could put a battery model there. You know, you could do everything from a basic, a more advanced battery model, or so there, we've got some lithium-ion battery models in the library here. We could put one of those on. We could put a source. Some of you might be using, say, a 3-phase source and a 3-phase diode bridge on the front end. That can be included. We can also include diode models here and look at the conduction and switching losses of the diodes in this presence and include those into the system if we want to. And obviously, if this DC bus voltage is now varying because of this, we will see the controllers working to maintain proper IDIQ set points, and we'll see the impact of that varying DC bus when we try and hit on the efficiency maps. So everything, again, that's a perfect example of why you need a stable control system, which is what the design suite will give you, is so that you can look at those sorts of simulations and look at your efficiency points at those points while ensuring that everything is working properly. Can you simulate a multi-level inverter? Of course you can. So inside of here, I've got a 6-pack device. If I wanted to go multi-level, you know, I just would build this up in the configuration that we want to. So multi-level is no issue. You should be able, this is 3-phase based. So these modulation waveforms, obviously you would need to change the modulation techniques, but there is, if we go to multi-level, there's lots of examples in our library that deal with multi-level converters, and if you want to do phase shift or level shift on the control schemes, that could all be included. It's very straightforward. For the controller, can we do auto tuning based on some test data? If you want to, you know, that's up to you. This is a template. You can edit it how you see fit. What the output of the design suite is, though, is it's stable and going to work based on what your parameters are here. Okay, so once you start fooling around with things to match whatever test data you might have, you know, that's when you start getting into extra design process steps. Let me just look through some more of these questions here. Oh, there's my menu bar back again. Is there test software which validates versus actual tests? So PSIM has been around for about 25 years now, and many people have published papers with regards to accuracy. Many people, JMAG has been a well-used FEA tool, and many people have compared PSIM results and JMAG results versus real-world results. So there's lots of information out there if you wanted to look at accuracy. There's a question, I think, Dheeraj, might be best for you. Is it possible to determine the hysteresis and other losses individually?
Yep, let me quickly jump in. Yes, it is possible. Actually, JMAG gives that breakdown. Perfect.
Okay. Dheeraj, I think I've answered most of the questions. If there's one here, if JMAG torque results and PSIM field-oriented torque results are not the same, which parameters could be wrong at the RT model? So that's a good question. So that all comes back to the control technique used. So right. PSIM, we're using MTPA, field weakening, and max torque per volt control. This is a fairly advanced algorithm. I'm not sure what, Dheeraj, I'm not sure if the JMAG RT model is considering max torque per volt control or what the criteria are in the transition between, if there's any how those algorithms are implemented with JMAG when you do that control systems, that basic motor efficiency pop-up in JMAG. Maybe you can expand on that.
Yeah, it's a similar, on the control side, it's similar in JMAG too. It constructs all three, MTPA, MTPV, and in between MTP, AV modes. But I think that there's a difference in the modulation because we have to keep in mind that we're using DC bus voltage as the input here. And it depends on how the modulation changes. What is the limit of the voltage that comes in? So there might be subtle differences with that.
Right, Dheeraj, this is the Mark. Let me chime in here. Now, the question is that if the PSIM controller, the output of that, and does not match the JMAG RT torque value, obviously, when people design the motor, and then the output of that is what's intended. Now, chances are, if it does not match, it's your controller, right? I mean, if you look at the controller, we try to use the known knowledge and design the controller. For instance, we, in the screen that we have here, we got the current loop bandwidth and the torque loop bandwidth set there. We all know that. Depending on if the gain is not the issue, their stability is not the issue, probably chances are they should match. And then in couple of that, you also have a PWM, the switching scheme there in the way. So the short answer is, yeah, I would trust the JMAG model more. But the thing is, they're just like any controller. I mean, you try to reach, to achieve the best target, the best value for the target, but still there will be some error there. So the JMAG model, I would trust them more.
Other questions that we see here. So we're coming up. We've hit the hour point. I think the organized. I have a little bit of extra time if there's more questions that are coming in. But I just want to let Sarah hop in here and give a wrap up for folks, and then we can stick around if there's some more questions that come in now. So please think of some final questions to come our way, or if you'd like me to go over something else, or Dheeraj, and then I think Sarah will just give you some housekeeping points here, which try and get in here towards the end of the hour.
Yes. Great webinar, guys. Thank you so much. And to the audience, thank you so much for coming today and sharing your time with us. There will be a quick survey popping up if you have a minute or so to quickly fill out those questions to help us improve our webinars and our content in general. That would be great. There you can also indicate if you want to be contacted by us for some additional discussions, or for more, maybe even from the sales team to inquire about buying one of those softwares that we talked about today. And of course, if you want to stay up to date with our webinars and other content like tutorials and so on, please go and follow us on LinkedIn and also the other social networks. On our website, you can also sign up for our news, so you get invited for those kinds of things, depending on the interest that you indicate in the form. So, yeah, if you enjoyed this today, we hope that you will come back to one of our other webinars. And for now, we wish you a good rest of your day and hopefully see you next time. And now back to the Q&A.
Thanks, Sarah. Yeah, so there's a question in here, Dheeraj, do you see it, about LDLQ, the spatial harmonics? I think Ryoko has just passed in some response there, but maybe you'd like to read that out and expand upon that a little bit more with regards to how that's all done.
Yeah, the question is based on the test of the motor inductances may be different from the finite element model. If you'd like to fine-tune the DQ inductances, is it possible to change the inductance table within the RT model in PSIM? That's an interesting question. I mean, basically, it's saying that if the finite elements inductance are off from the measured values, what do we do about it? So yeah, so you can actually import or export CSV files, but that's more on the performance itself, not the inductance values. And to change the inductance table, you need to go back into the JMAG RT library manager and change the source file from there. So that's one question. And I see there's a couple more questions on the inductances, meaning there's a couple questions from the same gentleman. Is the DQ inductances, are they incremental or what was the other term? Absolute or incremental, apparent or incremental inductances. So PM machines have PM flux in the D-axis. So to remove that value, the impact of the PM flux on inductance measurement, what we usually do is D-axis is incremental inductance and the Q-axis is apparent inductance. On the RT model, I don't think that's an option. There's an option to change. The second follow-up question was that our measurements are incremental for both. Can I modify to be an incremental value? No, because the simulation actually takes those specific operating point inductance values, and that's not based on what we can physically measure outside. That's the machine characteristic. But of course, for the analysis part, I think if you do the efficiency map calculation, there's an option that you can choose which values you want to output, meaning it's either both incremental, both apparent, or D-axis being incremental. All right, so...
Yeah. There's another question. I'm trying to understand what the question is. It has to do with phase voltages or back EMF. So in PSIM, in this simulation, yes, this machine model is generating a back EMF that one can measure if one wanted to. And obviously, the transition into field weakening is driven by the back EMF and the voltage drop across the input impedance. So there shouldn't be any. All of that is working properly and is considered as part of these models. So if we didn't have field weakening, if we didn't have max torque per volt control, the speed torque curves that we're getting here, we wouldn't be able to achieve these curves and these profiles if we weren't using those properly. And we would also see that if we tried to run this machine without those, try to do the simulation without implementing field weakening, without implementing max torque per volt control, we would quickly hit a wall where everything would kind of go unstable, where we'd be trying to drive the machine and not have enough DC bus voltage overhead to get there. So all of that is visible in simulation, and we would be able to see it. And if we didn't implement these algorithms, it wouldn't work at all. There's a question about the impedance matrix for JMAG.
Let's see which one.
Does JMAG have the capability to calculate impedance matrix?
It does have inductance matrix that can be output, but that's not usually recommended for PM machines. Obvious reason, again, the PM flux is in one of the axes, meaning it's rotor position dependent, so you won't get a symmetric matrix if you have the PM flux there. But otherwise, you could always back calculate the inductance matrix from DQ voltage. That's the DQ inductance matrix that comes out of JMAG.
So another question comes through. Can we generate code to flash this to a microcontroller? Yes. That's the other trick of PSIM, is to generate code for TI DSPs or for a PE-Expert4 control system, which is a very high-performance motor control system. A little bit outside of the scope of this webinar, but yes, we can basically take a control algorithm and then chunk it and then plug it into a microcontroller. But it does actually lead me to another, taking that as a tangent. What we have here are, we can see that these are control blocks. So inside of this subcircuit, we've got, let me just back up here, kind of try and show more than one thing at a time on my screen. We've got a control algorithm implementing our max torque per ampere field weakening. We've got our current controllers here. We've got transformations. Conceivably, PSIM is a runtime compiler. So we could replace all of this. We input our 3 inputs and 3 outputs, or have some number of feedbacks. So all of our feedbacks, currents and voltages, and then come out with our modulation waveforms over here and connect this up. So we can insert our own custom C code here. And we could then include that as part of our simulation. So if your control guys or have C code that runs, can be inserted into here to control it, and then you can still, instead of using our motor control design suite control values, you don't necessarily, you can still use this template then to come up with and start looking at, running scripts to look at efficiency maps and run that JMAG RT file. So you're not limited to this schematic isn't locked again. You can edit it however you would like. Obviously, once you start editing it, if it stops working, that's, you can send us a message to ask for help, but I mean, that's kind of, that's your thing to try and figure out. Okay. Okay, well, I think, I'm just looking through the questions list here. I think we've gotten to everything. Anyone, Diraj, any final comments, or Mark or Sarah?
No, I think, yeah, thanks a lot for all your help in setting it up, and thank you for all the attendees and all the very interesting questions that we came across here.
Yeah.
Hopefully we answered everything.
I think that was a great webinar. Thanks, Diraj. Sarah?
Thank you.
Thank you, Sarah.
Yeah, and everybody else, maybe see you at the next one. Also check out PowerSys website and our website for more content. For example, code generation content and so on. We have other stuff, and we will also have more stuff in the future, so it never hurts to follow us and check out the content once in a while. But for now, we're going to say goodbye and wish you a great rest of your day, and see you next time.
Thank you, guys.
Bye.